anything enough.
Great.
I'll only say appropriately.
Perfect. Well, with that tone for the seminar, we're very happy to have Kim here.
Is it the end of the seminar?
To tell us about one very exciting and popular avenue for pushing down the massive dark matter we can detect. So, Kim, take it away.
Thanks, Seth, for the introduction. Thanks for having me here. It's great to be here at UChicago. So what I'll be telling you about in this talk is the work I've been doing in my postdoc, particularly probing dark matter nuclear interactions in the Sub GeV dark matter mass regime. And the talk will be based on 2 papers that I've written with Ruben Essig and collaborators at Stony Brook. So as the outline of my talk, I'll very briefly talk about Sub GeV dark matter detection, what is important when we try to probe lighter dark matter compared to our conventional approach. And then I'll introduce the Migdal effect. And then I'll talk about a calculation that we did specifically for the Migdal effect in semiconductors for low momentum transfers that allows us to connect the data that we're taking right now to our theory that we start with. And then towards the end, I'll talk about next generation detectors that try to push down the dark matter that we're sensitive to even lighter dark matter, and considerations that are important for those type of detectors. And then I'll conclude with a summary and outlook. Okay, let's talk about dark matter direct detection. So why are we looking for dark matter? We know that about 85% of all the matter in our universe today is dark, and what we as particle physicists are trying to probe is we're trying to see how does this dark matter interact with our matter that we know and understand well. And what we're doing in dark matter direct detection is directly looking for those interactions. And in particular, I'm focusing on interactions between dark matter and nucleons, so protons and neutrons. And the conventional dark matter detectors that we know, for example, xenon 1-ton, what they're looking for is they're looking for nuclear recoils. So the idea is we have dark matter coming in, it's heavier than a GeV or so, and then, oh, is everything looking?
No, I just want to turn this makes.
Can you see well enough?
Or do you want?
Or do we need to?
No, I think it's fine. I'm just.
I think it's okay.
It's okay?
Yeah, it's fine.
For us, it's okay.
If it's okay for you, I said I'm good.
Good.
Okay, so the idea is if our dark matter is roughly heavier than the proton mass, so if it comes in and it hits something, then we'll get a sizable nuclear recoil here that we can measure and that we can pick up. And those elastic nuclear recoils are of the order of keV. But a complication when we're trying to look for lighter dark matter is that basically what's happening is that our dark matter is becoming lighter. So just by momentum conservation, if it comes in and it hits an atom, the recoil is becoming smaller and smaller. And that is difficult to measure. It's difficult to build detectors that have those thresholds. So the name of the game when you're looking at Sub GeV dark matter is to look for inelastic excitations. So for example, what can happen is if we have a lighter dark matter coming in, we can ionize an atom. And that requires much less energy, order electron volts, but thus this ionization is easily measurable. It leaves a striking signature. We know very well experimentally how to measure ionization. So when you go to lighter masses, those are the type of signals that you want to optimize your experiments for. And going even, yes?
Could you explain why that sort of stops working around MeV?
Yes, so we know roughly what our dark matter velocity distribution is in our locally, so we know that's 10 to the -3 or so. So then you can just ask, if we have dark matter of a certain mass coming in, what is the energy available, just kinetically? And then eventually you fall below the threshold where you can still get ionization. But what we can do even for lighter dark matter is we can look for another type of inelastic excitation. And here I'm highlighting phonon and multiphonon excitations. So if we go to condensed matter targets, such as crystals, what we can excite are of an even tiny dark matter comes in, and with tiny, what I'm meaning is that it's very light here, can come in and excite a phonon in your detector. And phonon energies are very low. They're of the order milli-electron volts. So you can excite phonons or multiphonon modes, which are just vibrations. You can think of those as tiny heat deposits of your dark matter. And those are also inelastic excitations that we can look for. In this talk, I'll be focusing on both of those, and I'll be starting with the looking for ionization. And in particular, we can say, okay, how can we get ionization? There's this very trivial case when we say, okay, dark matter couples to electrons directly. In that case, it's very easy to get ionization. But it turns out that you can also get ionization if you're exclusively coupling to nucleons. And how do we get that? And the idea here, this is the Migdal effect. It's called Migdal effect because Migdal in the 1930s was the one who first proposed this effect. And what the Migdal effect describes is that, and this is not only true for dark matter, this is true just in general, this could be a neutron as well.
Neutron, yeah.
Yeah, is that you have something coming in and it hits your nucleus. So you have a sudden recoil. So then what does that look like? In the final state, our nucleus is suddenly recoiling, and then nucleus is recoiling, dark matter is going outwards. And if we look at this in the nucleus rest frame, what it effectively looks like is that the electron cloud is getting a boost compared with your nucleus at rest. And what that induces is a small probability for a final state with an ionization. So in terms of rate, this happens rarely. Not every time you hit a nucleus, this happens. But when it happens, then you get this ionization signal, which is a striking signal, which you can look for. So knowing that this effect happens, and based on everything we understand in terms of physics, this is an effect that exists in nature, we should be able to take the data that we have from ionization and project it onto what it means for the reach of experiments that we have that probe dark matter. And in atoms, this is a well understood effect. So we, like I mentioned, we have a rate suppression because we have a small probability of it happening, but when it happens, then we can detect the signature. And to give you guys an intuition, this process for atoms, we can think of this as a process that factorizes into just the nuclear recoil cross-section times a probability to get that ionization in the end. And this is something that for atoms at this point is really well understood. So we can take the data that we have for atoms and analyze it using this Migdal effect. And this is something that has been done. A lot of attention has been on this in recent years by Ibe et al. And by another group et al. For example, how do we calculate this probability? And one approach is calculating your electronic wave functions. You're just calculating the orbitals of your atom, and then you ask what is the overlap, and then what is the probability after this Migdal effect happening of getting ionization. You can also obtain this information from data. This group here has shown that with photo absorption data, you can get a hold of this ionization probability. So in atoms, this effect is well understood. But what is even a more interesting detector than free atoms, especially in terms of ionizations, are semiconductors, because they have much smaller band gaps. So we can get an even better reach. Like electrons, we all know hydrogen, we need about 13.6 electron volts to get an electron out. But in semiconductors, the band gap is just order electron volts. So semiconductors are really like the ideal target that has the most reach for dark matter. So let's talk about how this effect looks like in semiconductors. How can we describe this theoretically? And here, this ionization part is, can we do the same thing that we did for the free atom with the wave function? Yes.
Yeah, just for the atoms, is there like all the theory calculation? Is there some experiments actually measure?
Oh, a very good question. I was just at Fermilab talking with Dan Baxter, and he's actually very actively working on trying to measure this effect. The Migdal effect has not been measured in nature to date. So it is a theoretical prediction that we think should be there. But there are two groups, one Australian group that it's called Migdal. This is the acronym for the experiment. They're aiming to measure this effect. And then also at Fermilab, there's an effort where they're putting in the proposals and trying to get funding to measure this effect, exactly to calibrate it for.
Yeah.
So it has not been measured with neutrons.
No, but that is ideally what you would do. You'd measure it with a neutron beam.
I see.
What's the original context for Migdal effect? Like why Migdal proposed this?
Probably because they discovered the neutrons in 1930s, and then they tried to extract all the information that you can get from neutrons.
But that for 90 years
Then they
there's
didn't do
no measurements? Like
So historically, I don't know the context of why Migdal started thinking about it, but I know that this is a homework problem in Landau and Lifshitz.
2 lines, trivial.
Imagine you have a sudden recall, like calculate the ionization. So
but like neutron people do all the scattering of material all the time.
So this is not hard. This is not necessarily a trivial measurement. And Dan Baxter actually told me about all of the difficulties. Neutrons usually have very high energies. It's easy to make a high energy neutron beam, and then it's difficult to resolve the signal. So one actually needs a clever experiment that's exactly designed to measure this. You're not going to see this when you're trying to measure something else, just as a byproduct. So how can we generalize the calculation that we understand from atoms to semiconductors? And there are 2 pieces here that change. So one is our ionization probability now depends on our electronic band structure in a semiconductor. And that is non-trivial. Our valence electrons are non-localized, so we cannot just simply calculate our orbitals and then do this overlap. And very recently, there has been a lot of progress on this, particularly Knappmann, Kozarczuk, and Lin in 21 proposed a formalism on how to describe this. And their idea is to describe this as a 2 to 3 process, an old-fashioned perturbation theory, where you split it up into 2 interactions. One is your dark matter nucleon interaction, and this is just we can just write down a Yukawa like a heavy mediator Yukawa interaction, or like a light mediator Yukawa interaction, plus the interaction between the nucleus and the electron, which is just your usual Coulomb interaction. And then you can solve this in old-fashioned perturbation theory. And what they have shown is that you can relate the properties that encode here this ionization probability in the dielectric function of the macroscopic dielectric function of your material, and that you can encode in the electron loss function. And this is a quantity that has both been measured and theoretically studied for a long time. So this is a quantity that we have a good handle on. So this is the part that has been understood. But what I want to focus on in this talk, and this is the part that we worked out, is that there's another part that actually changes. And that is not only the ionization probability, but the way that your nucleus responds. And the intuition between this is the following. And for a free atom, if we ask what is the state of our final nucleus, we can just describe it as a plane wave. It's a free atom. But in a semiconductor, in a crystal, your nucleus is subject to potential. It's not a free atom. You cannot describe the final state as a free atom. And a big question in the literature that wasn't clear is how does one properly take this into effect, and how does this affect your total rates? And the work that has been done before, they treated their final state of the nucleus as a free plane wave. And this is an approximation that is really good as long as you are in a momentum regime where your nucleus got so much momentum that is as well described by a plane wave. But as soon as you get into the regime where it matters that your nucleus is in a potential, that approximation is just not a good one. Like, it's not describing physically what's happening, so it breaks down. And they indicated that here, the uncertainty, that they cut off their momentum integral where they know this is no longer a good approximation, and this is showing the uncertainty band here. But if we ask kinematically, like exactly the question that was asked before, what gives us roughly the range? Up to 1 MeV, we're still able to expect Migdal. If we just ask, isn't enough energy there to give us Migdal? We would expect there to be a Migdal effect in this entire range. And the question is, how do we quantify this properly in this range? And this is what I did and what I'm telling you about today. So yes.
Could you talk about the length scale associated with the quadratic dispersion? Like, what is the characteristic length that captures the parabola that you showed on the previous slide?
A lattice spacing, presumably.
Yeah, like what is physically for silicon or something?
It's usually expressed in order angstroms, I guess. Yeah.
I think.
Order angstroms. Yeah, 10 to the negative 10. Yeah. Good question. I'm thinking more. Of course, there's a physical length scale. I'm thinking more about this in terms of momentum and energy scales, and those scales I'll introduce in a second. Okay, so if we ask, so this is here is a sketch of kind of the kinematic regions that we're having. Up here, I'm plotting the momentum transfer in keV, and down here the corresponding dark matter mass, and this is just again assuming a velocity of 10 to the average velocity of 10 to the negative 3. So then, if we're asking if we treat our nucleus as a free nucleus and just use the plane wave, where does that approximation break down? And that is here denoted as the free ion approximation. There's an approximation that does slightly better, and that is you can treat both your initial and your final state as a free atom, or you can treat your initial state as the ground state of your harmonic crystal, and then your final state as a free atom. That is what is called the impulse approximation. Both of them break down at roughly the same scale, but one does slightly worse than the other. And then what I'm also showing here is what we did in the end to describe this regime is we used an effective field theory approach. And the regime in which our effective field theory approach is valid is this entire regime here. So what we're able to do is we're able to effectively bridge the expectation that we have for more massive dark matter and reliably calculate all the way down to the smallest masses. Yes, and what I'm meaning here with harmonic, what that means is we're just our nucleus is in a potential that we approximate as quadratic, but there can be higher order anharmonic corrections to this. So this denotes on where it is reasonable to describe your crystal as harmonic to a very good approximation. And this incoherent approximation, what this tells you is, does it make sense to treat our scattering event as localized on one nucleus? And when do we start, when does it look like you're scattering off the entire lattice rather than at a local site? And what we're finding here is for the entire regime of interest, where we're kinematically able to excite a Migdal electron, we can treat everything as incoherent. So this is a reasonable treatment in this regime. So by using
below 0.5 keV, you cannot treat it as a.
Yes, because then the momentum transfer, if you just ask what is your interaction size, it starts being larger than the spacing between
500 EV, right? That's 500 EV.
500. No, this is 0.5 keV.
Yeah, so it's 500 EV.
Electron mass.
No, this is a momentum transfer. Right? Q is momentum transfer.
Yes.
Right. So I'm just trying to see how big is 500 EV.
So yeah, what you're basically comparing is you're comparing this to 1 over A, where this is your lattice spacing, and if your interaction starts being larger than the lattice spacing, then you're scattering coherently rather than just over one of the nuclei, and that happens roughly there. Okay, so how do we do this in effective field theory? So so the tricky thing before was, how do we describe this final state? So what we did, if you do this in old-fashioned perturbation theory, there are 2 diagrams that contribute to this process. You have an advanced and retarded diagram that contribute. Where here, this is your incoming dark matter, this is your incoming electron, and this is your lattice that you're scattering off. And the interaction is mediated basically by your excited lattice. And what we found is that there is a separation of scales, and that is exactly that your ionization energy is larger than your typical lattice excitation energies. So you can integrate out these intermediate modes, and you can express this in terms of an effective lattice Hamiltonian, where the effective lattice Hamiltonian is quantified by this operator, which depends on what exactly your initial interaction was between your dark matter and the nucleus. And the interactions that we assumed here are Yukawa interactions. So this is fairly general. This would hold up both for scalar and for vector-mediated interaction for both light and massive mediators. And so what we find when we do this, integrating out these intermediate modes, it greatly simplifies your calculation, and we're able to, in the end, derive an expression for the cross-section that only depends on the crystal dynamic structure function. The crystal dynamic structure function is this function here, and what in condensed matter systems, dynamic structure functions are very universal. And what do? What they tell us, for nuclear recoil, we have an exact relationship between our momentum and our energy deposition. We know exactly, like, the energy is related to the momentum transfer by q squared over 2mn. But in a condensed matter target, this relationship breaks down. Well, what happens is that for a fixed momentum, we have a finite probability of a variety of energy transfers that can occur in your condensed matter material. And this probability is exactly what is encoded in your dynamic structure function. And the nice thing about this is that this is a quantity that is directly measurable. So because we can express our expression in terms of this dynamic structure function, at no point do you need to make any explicit theoretical assumption about what the final state is of your nucleus, because you can directly relate it to a quantity that you can measure really well. And so if we compare this, how it looks in a crystal versus how it looks in an atom, we would just replace this with our delta function that conserves energy and momentum. So for an atom, there's really only one point where we get an energy deposition, and in a crystal, this is spread out. The nice thing is that we can calculate this, especially under the assumption of an harmonic crystal, because when we have harmonic oscillators, everything is simple, and we know exactly how to calculate things.
This is the process, or this is the cross section for the whole process. This is the including the electron final state. Oh
yeah. So the electron final. So this is just the proportional sign. The electron final state is still encoded in the electron loss function, which is another measurable quantity. So right now I'm only talking about how the nuclear response changes. If we go, I went too far. Sorry. I'm talking only about how this part changes, but the ionization probability is still there, and it's also something that can be related to a measurable quantity. But the big question was what happens to your estimate when your recoil changes.
So the factorization is because these two happens at different time scales. The ionization and the...
Yeah, that's one way to think about it. The ionization is a fast process, so it happens on shorter time. It's a higher energy process than the lattice excitations, so it happens on shorter time scales than the lattice excitations. Okay, so here's where I was. Okay, so the dynamic structure function in a crystal is something that has been really well understood in the neutron scattering literature, and especially under the assumption of having an harmonic crystal. This can be calculated, and there's something that I want to highlight here. This factor here, this Debye-Waller factor, it intuitively what this tells you, it compares the scale of your momentum transfer with the size of the wave function of the nucleus in a lattice. So in a nucleus, it becomes spread out, just as you in a lattice it becomes spread out, as you would expect for an harmonic oscillator. So this kind of is your order parameter that kind of tells you what's happening. And if we have the phonon density of states, which the phonon density of states is a quantity that very much is material dependent, but it's something that is both calculable and measurable. If you know this, then one can basically calculate this dynamic structure function order by order by evaluating this correlator. And what we then find is basically we have one elastic piece. This here encodes just the elastic scattering where you don't deposit any energy that corresponds to the entire crystal recoiling. Then you have your single phonon response, and then you have a higher order multiphonon processes. And those fully quantify your dynamic structure function. And those, to get the multiphonon terms, they're related by a recursion relationship. So if you know your phonon density of states, you can recursively calculate any higher order component in your multiphonon scattering. And let's get a feeling of this dynamic structure function. It's a function both of Q and of energy. And for fixed Q, it's the probability of what does your energy deposition look like. And the Debye-Waller factor is what controls roughly what regime you're in. And what I'm showing here is when the Debye-Waller factor is very small, then for an harmonic crystal, what we find you're actually dominated by the elastic response. So dominantly, you don't produce phonons, but you still have some probability of producing phonons. Versus for a free ion, you would expect a delta function somewhere exactly, so you don't have a probability at all that your energy deposition is spread out. And in the impulse approximation, an impulse approximation is basically taking your delta function and spreading it out to be a Gaussian. So this is this dashed line here. And as we look at what happens as we vary the Debye-Waller function, we see how the weight shifts. So the other approximations are not good, at least in this regime. So what actually tells you most physically what's happening is this harmonic approximation. And we can see how the weight shifts. So you still have some elastic piece, but now it's more likely that you excite phonons until eventually you get something where you have still a small elastic piece, but you're kind of dominated by all these higher order multiphonon pieces. And eventually, when your Debye-Waller factor is really large, you start being very well approximated by this impulse approximation. You start looking like a Gaussian. And if you take this to being really large, then the fact that the Gaussian has a finite width doesn't really matter, and you basically look like a delta function. So this is how you progress, and to actually calculate the Migdal rate is you need to integrate over Q. So you need to know how the dynamic structure function looks like at every point in Q. Yes?
So at the peaks in the structure factor, like when it goes on resonance with like multiple phonon emissions, like here you have these very nice looking peaks, for example, in the lower left corner.
I wouldn't necessarily think of it going on resonant. It's more, you take this initial distribution, it's your phonon density of states is your input, and then you keep convoluting it. And eventually, if you eventually at some order, a higher order of convolution, you're going to smooth out all of the material dependent features that were there in the beginning. But here you're not quite at.
So what is happening why is there like sharp peaks? Like what is the physical underlying physics of like the fact that suddenly your structure factor shoots up? In the harmonic
it comes from those pieces here. It comes from that your initial phonon density of states has discrete features. So whatever the features are here, that's what's they're going to get inherited in those intermediate terms. And if you change your initial input, those will have very different positions, so forth. So what you can think of this is a sum of all your multiphonon terms, but the weight is shifted towards higher order multiphonon terms, and those terms have these features. Thank you, that's a good question. Okay, so let's look at what results we get. So we can we've fully quantified this. So now what we can do is we can calculate the rate that we would expect from the Migdal effect using our framework. And this is what we're showing here. So the red curves and the blue curves are our projections for 100 gram per year germanium and 100 gram per year. So here we're saying sensei, this is a silicon detector, and we're comparing it to other measurements. So xenon 1 ton on xenon 10, they have much less sensitivity, and similarly, like 100 kilogram per year, a xenon detector would also have less sensitivity. And indeed, the semiconductor targets do have the best reach that we can think of. And here, this curve is actually so Sensei has already taken a lot of data. So Sensei does have a rate of ionization events. So now having a reliable calculation of what this effect looks like in this regime, we can take that data and forecast what the reach is. And that is somewhere right here. And we can do that both for a heavy and a light mediator. And we can see if we use the impulse approximation where this is showing the uncertainty band that we previously showed, where you cut off your momentum integral, where you know that your approximation is no longer valid. For a heavy mediator, it still does a decent job, but actually for the light mediator, cutting off the lower part of your integral, where you can't trust your theory anymore, but you actually dominated by your lower momentum processes, that significantly underestimates the rate. So we were the first people to put this on very robust footing. But now you could ask, okay, so what happens if we just treat it to be a free ion and we just extrapolate it and we don't cut off our momentum anywhere because we just think it's right?
Remind me what Sensei is.
Oh yeah, so Sensei is a 2 gram silicon detector. The measurement that's shown here is at the Minos Hall in Fermilab, and they're using a Skipper CCD technology to read out ionization signals.
And Sensei sounds like a Japanese name, so it's not, right? Sensei.
It's on purpose.
Sounds Japanese, huh?
Japanese
Teacher.
Why did we name it Sensei?
Yeah.
Teacher.
Oh, it's teacher. Oh, it's teacher.
That's
teacher. Yeah.
Sensei.
or politician.
Oh, politician. No, forget. Teacher and politician are the same? Oh my God. Okay, continue.
Okay, so now that we've done all this hard work and we calculated this very exactly, very properly, one can ask, okay, what if we, yes?
If you go beyond the 100 MeV, like do they like also converge like impulse approximation with it?
Here they do for the heavy
I mean
mediator.
for the light mediator.
For the light mediator, no, because you cut off a part, like in this approximation, you cut off your low Q regime, but the light mediator gives you a light Q enhancement, so you're always cutting out a significant part of your signal. And this cutoff, this IR cutoff, it's completely artificial, right? It's like you're like, we don't know our theory uncertainty, so we impose a cutoff, but it's not physical in the sense that there's a reason for there to be a cutoff.
Yeah, so but in principle you can increase the band. I guess the uncertainty is given the cutoff.
Yeah, this is exactly like how aggressive do you choose your cutoff, and that is basically in terms of the Debye-Walla factor, you're varying by like a factor of 3 to 5. And as we have seen, as you go to 1, you start getting these. You go away from the impulse approximation.
I think it seems to me that in these two cases, the characteristic line time scale or length scale for these two scattering processes are different. Depends on your heavy or light mediator. For the light mediator, it's like the cross section is 1 over Q squared. The heavy mediator is just some 1 over some mass, like the some power. And I'm just wondering, so since you're going down to like pretty low Q, so one of them will become dominated by the infrared, like the light mediator is. But by light mediator, you mean mass is less than Q, or?
Yes, yeah, with the light mediator, I mean, taking the limit where your mediator mass is negligible compared to Q, so.
Yeah. So then for light mediator, it will be just dominated by the lowest Q you have, and
Yes.
that seems to be pretty big in comparison with. So as one of your earlier figures showed that at some point you will be not even talking about it will be comparable to the size of the lattice and.
Oh, so your worry is if you get down.
I'm just worried about, so you're making this assumption about there's a separation between two time scales.
Yes, no.
Does it always work, no matter what?
Yes, this is a very good question, and this timescale question also with the light mediator is something that people have started to look at also for the atomic case. Is there something going on with the timescale where it would change with the expectation of a light mediator? So this is a work in progress right now, actually, that Reuven Essig, one of my collaborators, is doing with a separate group, and they worked out this timescale issue in a lot of detail. And this is in progress work, so it's not public yet, but they have found that there's no timescale issue and that one can.
Okay.
Yeah. But thank you. That was a very good question. Okay, so we've done all this work. Now you can ask, okay, what if we're just completely naive and we just take our free ion approximation, we just use it anyway because we don't care? How do our results differ from that? And so what we actually find is that whether you do it completely rigorously and correctly, or you or you just treat everything as a free ion, there's no difference in the differential rate. What do I mean by differential rate? By differential rate, I mean if you don't care about the observable of how much deposit do we deposit in ionization, how much do we deposit in our detector, if you don't care about the detector and you just integrate over all the possible depositions to our detector, so you just care about the ionization, which is what we currently have measurements of, you don't get a difference. And so why is that true? So the reason for that, it really comes down to a sum rule, or what we end up doing in our calculation is you end up integrating. You have basically an integral over E here, over the energy, and if you integrate, you can think of this as the probability for a fixed Q that you get an energy disposition. If you integrate over that probability, you're going to get 1. So the difference, though, is that you do have a kinematic cutoff. You have a finite amount of energy that can go to your ionization or to your phonons. So that can cut off your integral early, maybe before you reach 1. But if we look at the kinematics of our situation, our ionization energies are order electron volts. Our phonon energies are order milli-electron volts. So we don't get a phase space suppression from that at all. And once you integrate over dE, this factor is always roughly equal to 1. So in this observable, you actually don't get a difference here. But the important thing, and I want to highlight this, there was a group this summer that claimed that there was a large difference. So this issue was actually not exactly settled. So we communicated with them, and it turned out that they ignored the elastic part of your scattering, and you become dominated by the elastic part. So now this is a settled issue. Like, we know that we can trust this estimate. And previously that was not clear of what we would expect here. So now let's talk about the exclusive observable. So there is now also an observable where we can ask, what is our, we can have an event, a double event, where we get ionization and a phonon excitation, a doubly inelastic event.
But as you say, the Migdal effect has never been measured, right? Maybe it's not true. Maybe that.
Yeah, I mean, we were just talking about this. If they try to measure and they don't find it, then that would actually be really interesting,
Right,
because
really
there's something about our physics.
Cancelled by dark matter. Destructive interference.
Controversy.
Right. So can only be detected the Migdal effect and Migdal effect.
Yeah, that would indeed be very interesting. But
No, it was a joke. Okay, sorry.
Okay. let's talk about our exclusive variable. So right. So we can ignore the dashed lines here. So what I want to highlight is we can ask if how does our spectrum look like if we just use it as a free ion? And what we find is that you severely underestimate the threshold of energy deposition that you get just in that approach. If you do it properly, it ends, and let's say you build a detector that has a threshold right here, like being able to measure 100 milli-electron volts. Then if you falsely approximate this as a free nucleus, you expect that you could never measure this, versus if you actually take the material effects into account, you do find that there's a finite probability for energy deposition at much larger energies. And there are actually future generation detectors right now that are under development, where people are working really hard to lower our sensitivities to be able to measure these phonon and multiphonon signals. So potentially in the future, this could be observable, where you try to measure both ionization and phonons. And that would be a very interesting multi-channel signal that would potentially allow you to reject backgrounds very well. And if you do that, then you need very much an accurate description of your crystal, and then our framework can be used to quantify this. Okay, so summary is, so the calculation of these rates is important in order for us to be able to interpret our data. We're taking data, so what does it mean on what handle do we have on our theory, and also how does that connect to other experiments? So it is important both to measure it experimentally, but also that we have our theory calculations under control. And we used an effective field theory approach to extend this description to the lowest dark matter masses. And this is nice. We're able to connect things to observables directly. We don't have to make any explicit assumptions. And but if you only care about ionization for right now, you can just use the free ion approximation and spare yourself the trouble. And but this will be important to accurately quantify lattice depositions as well. And if we can measure them, then you very much need to use this framework. And this may be important for next generation detectors. So how am I doing on time?
15 minutes.
Okay, so I have a second part.
Equally long.
Excuse me?
No. Equally long.
I'm wondering, are there questions at this? If there are questions, this would be a good point to
Why
start.
don't you give us a summary of the second part?
Okay, I'll,
What
yes.
is the second part about?
The second part was about the next generation detectors. Yeah, I'll tell you very briefly, maybe we'll skip the details. Next generation detectors exactly try to measure phonons and multiphonons. But there's one thing really important as you try to play this game here with these small excitations. So milli-electron volts is extremely small amounts. And this is already something that has been important for order electron volt events. Your backgrounds become so important. In order for you to be able to use this to do dark matter physics, you need to have an extremely good handle on the backgrounds that you expect. And for phonons, this becomes even worse, because what is a phonon? It's a tiny amount of heat. There's tiny amount of heat everywhere, right? So if you just have a photon pass you through a detector, you can get a tiny amount of heat. So experimentalists are working really hard to get the sensitivity down there, but a big part of us understanding how well we can use it for dark matter is understanding the backgrounds. And that is something that we have worked out. So you can ask, what do you expect just the photon background to be in your dark matter direct detections? And what Alan Robinson has shown is that from coherent scattering and coherent over the electrons of your atom is what I mean in this case, not over your crystal. So he's assuming just a free atom with nuclear recoil energies, and you get a large enhancement from coherent scatterings that start becoming really important, and that could drown out your signal. And the assumptions that he's made we're basically assuming 0.04, experimentalists call this DRU, it's counts per kilogram per day per keV. And what you can interpret this as, so if we have photons, they have high energy, they can leave Compton scattering events, and that we see. They're very spectacular, they knock out an electron, and we measure it. And in experiments, we can classify how large this is. And if we go to Fermilab, for example, the Minos Hall, it's 100 meters underground, they get about 100 counts per kilogram per day per keV of gamma rays, so quite a lot. So this really is the state of the art, the best that we can do if we go to SNOLAB or other really deep underground detectors, much deeper than these 100 meters, then we can get this down to this rate. And what is this rate dominated by in the end? Everything is radioactive, also the detectors that we built, the bananas you eat, in a very small amount, not a lot. But for these experiments, this becomes very important because you still have some contamination in your detector. And so what we did is we quantified what these structure effects look like, exactly what are the phonon backgrounds that you expect. And I will, in the interest of time, I'll skip the details, but I'll summarize the main story for you. The tricky thing about photons is they can come in and have a Compton recoil scattering, and you get an electron, it's really loud, you know it was there. But the more tricky thing, and this becomes more tricky the higher energies your photons are, and with gamma rays, I mean order hundreds of keV to MeV energies. Your photon can come in, it doesn't Compton scatter, and it has an extremely forward scattering event. And that extremely forward scattering event leaves a tiny energy deposition, and that exactly looks like a phonon. And you'll never know that it was there because it didn't scatter again. And this is really tricky. And this actually leaves, assuming this very state-of-the-art shielding capabilities and purity capabilities that we have right now, this leaves actually quite a large background. It's dominant over the solar neutrino background that we would also expect to excite phonons. And in order for these experiments to be successful, one needs to basically build an active shield around it. You're not able to just veto it with your detector itself. So when one constructs these, this is a dangerous background to keep in mind.
And don't bring bananas into it.
Yeah, and don't bring your bananas into the lab. Exactly. Okay, so very good. So with this, I'll actually conclude. There's one last thing that I want to highlight, and that is yes. So my collaborator will be here next week, and he'll be giving a talk on a topic that I think will be very interesting for particle physicists. In particular, he'll be talking about how dark matter freezes and produces large isocurvature in the early universe, and this will be at the KICP. So I just wanted to mention it. Yeah, thank you so much.
Thank you, Kim. Are there further questions?
So the future detectors people are working on right now. So then, and Sensei, what is the status of Sensei? Sensei is running right now.
Yeah, Sensei is running. So Sensei is running right now at Fermilab. This is the Sensei at Minos. They're actively taking.
But they're going to move it.
They've already also have maybe prototype's not the right word. They also have a running version of Sensei right now in SNOLAB.
SNOLAB.
And that is very significantly cut down actually on the background events they observe. So Sensei right now sees a large amount of single electron events that they don't really understand what the backgrounds are, and that is limiting sensitivity. So you can do the most constraints with the 2 electron bins. So I put it into SNOLAB, and that cut down the backgrounds in the single electron bin, but they're still there. And there's a lot of work going on actually trying to exactly understand where they're coming from.
Thank you.
Thank you.
So can I try to make sure or measure how far I misunderstood you of the ionization process from a condensed matter perspective? So a particle comes in, a dark matter particle, which shakes up the lattice and creates a whole bunch of phonons, which is what this dynamic structure factor describes. So then the phonons decay into particle hole pairs. Is that the process that you're describing? Or
Yes, so a very good question. So actually the other group that has also worked this out, which initially forgot their elastic element, they exactly used the formalism that is closer to the picture that you have in mind,
Yeah.
where rather than writing down the Coulomb interaction, they quantified it through being mediated by a virtual phonon. So
Right.
that's another way of thinking about it in that regime. Yes.
But what's confusing me is that I didn't see any electron phonon coupling in your work.
Yes, because that's not that's an equivalent picture. That's a different formalism. And we didn't utilize the electron phonon coupling, but both end up being equivalent using the electron nucleus Hamiltonian in terms of the Coulomb interaction. Because both in the end, so I think that comes down to the part that I didn't focus on. It's the probability of your ionization,
Right.
and that you can relate to the dielectric function in your material,
Yeah.
the electron loss function, and you get that out in both formalisms in the end.
Okay. But the reason I feel I misunderstood or missed something is that it seems that the only thing you need from the crystal physics is the dynamic structure factor. But it didn't seem to need anything about its electronic structure. I mean, other than, let's say, the bandwidth or just the energy scale. Which, of course, I mean, is what determines the electron phonon coupling. You didn't seem to need that input at all in your work.
Let me make sure I understand. Can you restate?
So did I understand correctly that the only input from the crystal physics that you used is the dynamic structure factor?
Yes.
So therefore, it does not tell you anything about how the distortion of the crystal gets actually coupled to the electronic excitations of the crystal. That's the part I'm missing. Which should describe your ionization process, right?
Yes, so I think like the key aspect is like we factorized those two pieces into one.
Right.
So I think what you're saying is more fundamentally, there exists a structure factor that
Right.
takes both effects into account, very precisely. That then has your electron wave functions and your nuclear wave functions in initial and final state.
Yeah.
And what we did, we factorized those into like your electron initial and final states and your nuclear initial and final states. And then we were able to put the electron piece just in the probability and put the nuclear piece in the nuclear dynamic structure function.
But the electronic piece comes from the single ion physics, not from the crystal physics. Is that correct? So the second factor, the ionization factor, that only knows about the single ion physics, doesn't know about the detailed band structure of the crystal, does it?
No, it does. It exactly does through the electron loss function.
Of the crystal?
Yes.
Oh, okay, I see, okay. But that's
Yeah.
experimental input.
Yes, and I think the electron loss function has been measured, but also calculated with ab initio techniques. So you use it as an input, basically.
So that's the thing I missed.
Yeah. Thank you very much.
That makes sense. Yeah.
For your detections, could you go back to one of your original one?
The original.
Any one of them. Where? Yeah, maybe this. So now you're going down. So I'm just wondering. So it's not about your work. It's just a generic question. So is there a target you're going after? Or just the lower the better?
Yeah, excellent. Excellent question. Yeah, there are. So I would say a priori, the lower the better, but there are also, if you're asking, can we connect it to cosmological, theoretical prediction?
Anything, yeah. So let's say, you wanted to, at some point you wanted to justify, we'll give you money. I think unfortunately in our field, the lower the better, may not be able to get enough money.
Yeah.
You need to justify like, okay, here is my target. I think it's a good benchmark. We'll there's a, there's a good chance to see something there.
I mean, I think there are two perspectives. One is the very much agnostic one, where one can say, what is the best that we can do with like about a year exposure, and that's the reach that we can reasonably reach.
Right. So I think this year will convince us, but
yeah, and that you should max out because we don't know where it is, so we may as well look with everything that we can, and eventually, like there are some cross sections we will never be able to reach just based on exposure. Then the more theoretically motivated thing is how can we relate models with nucleon dark matter scattering to cosmological benchmarks.
Any interesting benchmark? Are we going after some
I think there are a couple, such as
these are pretty big cross sections, right? These are
yes, they are, and they're unprobed, pretty big cross sections.
Yeah.
I think there are a couple. I'm escaping right now which models exactly. So actually, I wanted to look it up for the talk, and then I was talking to Seth and forgot. But that's an excellent question. Let me get back to you on this.
Okay. No, just my curiosity.
No. I mean, this is.
It's not just.
This is why we're doing it, right? Like we're trying to rule out well-motivated parameter space. So this is a very good question.
Yes, so suppose the formula to do the Migdal experiment. Besides, you see this effect actually exists. Like what kind of information you can learn, like to confirm some hypothesis.
Okay, so the what Fermilab was trying to measure is they're trying to measure the atomic Migdal effect at first. So this will not really tell you anything about the semiconductor, but what it will tell you that we have a theoretical handle, at least on the atomic case, because it really is like a standard physics prediction. Migdal did this semi-classically. Like you don't even need quantum. You get the same thing out classically, quantum mechanically, like with old-fashioned perturbation theory. So if they try to measure it and they don't find anything there, then that's the big problem. That means we don't understand our theory at all. If they do measure it, it doesn't necessarily tell us how large it is in the semiconductor. That's why we still need like those calculations, and maybe those measurements will motivate also future experiments in semiconductors.
Great. If there aren't further questions, then let's thank Kim again. We're going to go to dinner this evening downtown to get deep dish pizza. Downtown. My neighborhood.
Where?
My neighborhood.
Oh, what is it?
Let me, the YouTube doesn't need to know where I live.